In this video, I'm going to show you how to make plots that are pretty and tables that look more professional in R. And I'm going to be using a few different packages, but one of the things we're going to do is try to make a histogram like you see on the screen that also has a box plot overlaid on it to help visualize the distribution a little bit better, and has some annotations on it to give a little bit more information about the distribution itself. Uh, and then we're going to make some tables that look more in an APA style, like the one that you see, both for descriptive statistics as well as for model output from a regression. And we're going to use a few different packages. So on the next screen, I'll show you what those are. And I'll give you a moment here to get R pulled up and these packages installed so that we can begin. All right, so the first thing you need to do is make sure to initialize these packages. So we're going to use Rio for importing and exporting, ggplot2 for making plots look nice, and this has become sort of a standard for making plots in R. The psych package we're going to use to call the describe function so that we can get the summary statistics. And then we're going to use the kableExtra package in order to make a table look a little bit nicer from that describe function. And then sjPlot we're going to use in order to make a nice APA looking regression output table that's more APA style. So make sure to import the data. We're going to use the same data that we have in previous videos from the 2012 PISA dataset. And for this video, we're only going to be using PV1 Math, ESCS, and then we're going to create this gender variable female, because the gender variable female, which is ST04Q01, is ones and twos, and we need to be zeros and ones. So we can basically just subtract one from all of those, and I'm going to call that variable in this video female. So the regression example we're going to use will be ESCS, PISA's measure of SES, and the gender variable as independent variables, and the dependent variable being PV1 Math. All right, so let's jump into the histograms. So let's say you're wanting to examine some assumptions and want to make a nice set of histograms with some information to showcase to people. So we're going to use the ggplot function, and you could do this with base R if you wanted a quick and dirty histogram by just typing HIST and putting PISA $PV1 Math in parentheses after it. And it'll give you what you want if all you're doing is exploring. But if you're wanting to make it look nice and professional, ggplot2, the way it works is first, we want to tell the data set that we're using. So that one, I've called it PISA when I imported it. So put whatever you called your data set there. And then AES means aesthetic. So, and here we're going to tell it what the axes should be. So with a histogram, there's only one axis, so we don't need to have anything other than PV1 Math here. In other instances, there are other things you could add in here based on how you want the plot to look, and we can talk about that in additional videos with once you get the basics here. And then you could just simply say geom histogram and then put nothing in here and it would plot it. And the way that ggplot works is that you have a set of different layers, if you will, to the plot or the visual that you're creating that are separated by a plus symbol. So at the end of each of these, you should have a plus symbol. So we're going to make this look a little bit nicer by telling it color equals black and fill equals white. Color equals black, that's talking about the outside border of the bars. And of course, the fill is the inside part of the bars. And then we're also going to tell it to have a theme of black and white. Originally, it comes with a sort of gray background to the plot, so we're going to white that out. And this is sort of what you might do if you were going to submit this to a journal, so that there's less color being printed on a page if they're doing that. It also looks a little better, in my opinion, to have the white background. Um, and then you could make these different colors if you wanted to, if you wanted the fill to be blue or red. But we're going to keep it simple. So you could just stop here and do that and it would look nice, but then the labels on everything are not going to look professional. So that's what the next set of things are for, are the labels and the text formatting. So here we have plus labs and title equals, and in quotation marks, the title that we want above the plot. So here I've just put histogram of PV1 math distribution. And then plus Y lab, that's the label for the Y axis. You can just put frequency, or you could put count. The X label, the X axis label, PV1 math. And then the last two are just about text formatting. So theme, text equals element text. And then inside of that, we're going to tell it Times New Roman is the family. Face equals bold is going to make the text bold, and color equals black. And then theme, again, to change the plot title, because by default the plot title is left justified rather than centered. So we want and we want to change the size to make it bigger. So we can say plot title equals element text H just equals 0.5. This is the line of code to center it. And then the size equals 24. Based on how big the window size is for your plot, you may need to adjust this to a different size. But I've put it at 24 here. Okay, so once you do that, you're going to see this histogram here. So it has a nice title at the top. And you can also, by the way, change the size of the text for the labels on the X and Y axis. You can also change the text size of the labels for the grid lines. So the 0, 2000, 4000, 6000, you can change those as well. In fact, you can even add axis labels if you want to. So there's all kinds of things that you can do, but we're not going to get into that in this video. So it looks pretty nice, but let's say that we want to also see that box plot on there. So if we want to do that, we're going to add 2 lines to this code. So before we just went from the geom histogram line here to the theme black and white, but now we're going to add geom box plot. And you could just simply have nothing inside of here. You could leave this blank, and what that's going to do is make the box plot extremely tiny and put it all the way down along the where 0 is on the y-axis. So it'll put it across the bottom here, and that's not what we want to see. So what we have to do is tell it where to center the box plot. So here I put AES, open parentheses, y equals 5,000. So that's going to put it at the y equals 5,000 line, between the 4 and 6,000, and it will center it. I mean, it's going to be the same range as this histogram here. And then width equals 500. That piece is telling it how tall to make the box. So since these are going up with the grid lines at rates of 1,000, I put it at 500 so that it would basically fill the space of half of a grid line. And then I put the fill as gray. You could make this any color you want, or you could even have no fill at all. But by making alpha equals 0.7, it makes it slightly opaque. So the smaller that number gets, the more opaque the color is. So basically you can see through it to see what's behind it. And I've added and box plot to the title of the plot, because we're now going to have a histogram and a box plot. And when you do that, you are going to see this. So you can see that the box plot is see-through. You can see the lines behind it. That's what that alpha equals 0.7 does. It also makes the dots out here opaque, but there's so many overlapping. You can't really tell except for the ones that are far out on the left and right. So and remember, those points are representing outliers in the data. Okay. So another thing that you might want to add to this plot would be if you're trying to think about normality and whether your assumptions are met, is maybe you want to put, because there's a lot of white space on the left and right of this plot. So you could put the skewness and kurtosis values. You could put the mean on here so that it's, because this line in the middle of the box plot's the median, so we can see that. But that way you can sort of judge how far apart the mean and the median are and use that as a visual to help understand normality. So to add that, we're going to add a set of 3 different lines. So the first one, we're going to use the annotate function. And the annotate function allows us to add, you can add all kinds of things on the screen. You could add different shapes. We're going to add text. So if you call the annotate function and then type geom equals and in quotation marks type the word text, then we have to tell it where to position the text on the screen. So this might take some playing around sometimes to figure out exactly where it needs to be. By default, it centers it, so we're going to take that out. But basically what I figured with this was to put it sort of underneath the box plot on the left side in the open white space. So I've put it at x equals 50. So if you go all the way to the left, it puts it pretty far to the left, close to the y-axis, and then y equals 4,000. So that's where the first line of text will be. And as you add text underneath it, it goes down, of course. And then the label, because we have 2 things that we want to put in here, label is telling it what text to actually add. So in quotation marks, I've typed skew equals 0.2. This is the skewness value for PV1 math. And this /n, what that tells R is to paragraph down, basically hit the enter key and go to the next line underneath it. This is used mostly, I use this in titles because plot titles sometimes can get long if you want all the pertinent information included in there. Like for instance, we could have included that this data came from the PISA 2012 data set in the title. So we would need to put that as a line underneath it. And then type, and you don't need spaces here, notice. It knows to paragraph down, and then kurtosis equals negative 0.2. And I did put spaces on either side of the equal sign just to make it look a little nicer. And then you can change the size of the text. So I put size equals 8, color equals blue. And then so that it's not centered, because the annotate function does center by default, whereas the title does not. I know it's kind of strange, but so put h just equals 0. That means don't center. Put it on the left. Family equals times. And bold we have to control by doing this. Font face equals bold. So the theme elements that we added at the end of this in order to control the way that the font looks for the title and the axes doesn't control this annotate function. So we have to add that inside the annotate function separately. Then, so that will add the skewness and kurtosis to the plot. Then the geom v line, geom underscore v line. This means add a vertical line. So we can add a vertical line to the graph to show where the mean is. And so basically just grab the value of the mean and put in x-intercept equals and the value that's the mean, and it will add a vertical line. And by default, that line is pretty small. Like it's going to blend in basically with the histogram bars. So I put size equals 1, made it red using color equals red, and then line type equals dashed to help it stand out a little bit from all the other solid lines that are on the screen. And then we need to, we can add the value of the mean next to the line. So it's easy to tell what it is since it's not going to be exactly where an axis tick mark is. So to do that, we need to use the annotate function again to add geom equals text. And what I decided to do was put it at the top because it's kind of hard to see the text when there's lines all next to it, unless you make the text really big, but then it looks kind of awkward, I think. So you could do that, but so where I put it was x equals 465, and remember the line is at 456. So I just scooted it a little bit to the right, and where the y value is 7,500, which puts it above the bars at the top of the plot there. And then label mean equals 456.71, the actual value of the mean. I put size equals 6. It doesn't need to be quite as big as the skew and kurtosis. Color equals red, so that's the same color as the line. H just equals 0 to center it at the left. Family equals times. Font face equals bold. So all of those things are the same that were already there in the other one, except that I made the text size a little bit smaller. And then leave everything else the same. So these last two lines of code here are for the title and the axis labels and the tick mark numbers. And when you do that, you get this plot. And so you'll see the skewness and kurtosis values on the left and the mean at the top there with the dashed line showing the mean. And you can see the mean and the median are very close to one another. Even though it looks like it's skewed to the right, maybe a little bit, it does look pretty normal. So it doesn't have any red flags screaming that there's an assumption being violated. So then if we move on and look at this for the ESCS variable, basically I did the same thing. All the lines of code are essentially the same. Obviously I changed the title to include ESCS instead of PV1 math. And the X label needs to say ESCS instead of PV1 math. But also, you need to change the position of these text on the screen because the range for X and Y has changed drastically on ESCS because ESCS, remember, is a standardized variable. So for this, I positioned it at an X value of -5 and a Y value of 4,000. Change the skewness at kurtosis values here to match what the describe function told me that they were. Everything else I kept the same here. For the geom v line, make sure to find the mean of the ESCS variable, which is -0.31, and then change where these are positioned as well for that dashed line. So I put x equals -2 because that's a little bit to the left because it's skewed, so we can position it a little differently. And then y equals 6,200 to put it above the bars. And then the label mean equals, make sure to put the mean in there, -0.31. And the rest of this you can pretty much leave the same unless you had to adjust the size of any of these to make the title fit on the screen correctly. And when you do that, you get this plot as we wait for it to generate. And so you see the skewness and kurtosis here on the left. So we can see that nicely. And there we go. All right, so that's the end of what I wanted to show you. Well, actually, no, there's one other thing. So we wanted to look at the residuals too. So we have a model here with PV1 math equals ESCS plus female. So here, use the same code. You just copy and paste and change the values. So we need to put the box plot at y equals 5,000, a width of 500 again. And then make sure to change the title to be about the regression residuals, the X label. And then here we don't need the skewness or kurtosis values, I don't think. You could add those if you want. I didn't. But I added the line, the vertical line at x equals 0, because the residuals should be centered around 0. They do have a mean of 0 if you look at the describe function. So we can put the x-intercept at 0, add that line, and then in the next annotate function, make sure to adjust where the text is located to say mean equals 0 next to that line. Although you wouldn't have to in this case because we want to see that line at 0 anyway. It just happens that the mean actually is 0 of the residuals in this case. It should be, by the way. Everything else stays the same, and when you do that, we see this distribution here. And you could add skewness or kurtosis values here, but it's very, very normal looking. So I'll leave that up to you. If you want to do that, add that extra line for the annotate function. All right, so moving on to thinking about tables. So there's a few different ways to do this. You could just run these separately. So cable is the function that we're going to use in order to get these values. So if you just run this, for instance, if we're looking at, say, the residuals, so the describe function that is in the psych package, if you run that, you're going to get this list here, and that's nice. But it would also be nice if we could then take that and put it into a paper where it looks a little bit more nice. So to do that, we put that inside the cable function, cable with a K, cable. Add that describe function in here. We'll say format equals HTML, so it's easy to copy and paste. Align equals C. What that does is centers the columns. And then we're going to use what's called pipe functions. So what this does is just makes it a little easier to say, once you do that, wrap this other function around it. So this is just telling it to use the kableExtra package. And then cable styling, what this does, all this piece does is makes it show up in the viewer so that you don't just see a bunch of HTML code on the screen that you could copy and paste. So if I run this, what you'll see here is that it made kind of a nice little table. So we have at the top the statistics in bold, and so it looks pretty nice. And we could do that with PV1 math and then do it separately again for SES. But it might be nice to have them all at once. So if we look at the where these are located, so PV1 math, looking at names of the PISA data set, PV1 math is the second column, SES is the third column, and female is the last column. That's number 11, right? Column 11. So if we use this and we say describe and PISA, in brackets, we can tell it which column numbers that we want. So if we just wanted a particular row, we could do that, but we want to use entire columns of the entire data. So we put nothing here, and then a comma. So if you put nothing, it just knows to include all the rows, comma, And then this C open parentheses function allows us to tell it multiple different columns to pick from. So here you could put a comma. I used a colon. It means go from 2 to 3 and include everything in between. In this case, there happens to be nothing in between. So 2, 3, and 11. So when you run that, you'll see in the console box here, you get all three. So it puts them in rows. PV1 math is first because that was column number 2. ESCS is second because that was column number 3. And female is last because that's column number 11. If you want these in a different order, just change the order of these numbers. So I could type 3, 11, 2, and it would reorder these. So then we can use this and wrap it inside of this cable function that we've been using. So if we do that and we say describe columns 2, 3, and 11, and then we can add something in the styling here so that we can make it like Times New Roman font. So in this styling section at the end, so if we copy and paste everything and add that to it, then we get a little bit nicer looking table. And we see these rows of PV1 math, ESCS, and female. And there we go. So, and you can export this as an HTML document, and it makes it really easy to copy and paste or screenshot it into a document. So once you export that, you can open it in. When you open it, it'll open up in your browser. It makes it easy to screenshot it or copy and paste it. Okay, what about the model output? So now we're going to use the sjPlots package and a function called tab_model, which stands for table model, table of model output, right? So up here, when I ran the model, I saved the linear model output into into the word model, right? So down here, that's what we're going to do first. Tell it where is the model information stored. It's stored in the word model. So put that. And you could just basically close the parentheses there, and it would show you a really basic function. So I'll show you that real quick. There we go. So you'll see that at the top it says PISA dollar PV1 math, PISA dollar ESCS here inside the table. So we can make these things look a little better. And we can add some things to it. So you'll notice, for instance, that the standard errors are missing. The t-scores are missing from the table. So we have to tell it to show those things. So if we look back on the left here, show SE means show standard error equals true. Show the standardized beta score or the standardized estimate true. Show statistic equals true. That means show the t-score in this case, because that's what's associated with these estimates. Show the degrees of freedom equals true. We can add that. And we can use this function, collapse.se equals true, which forces it to put the standard error in parentheses after the estimate instead of in its own column. So if you want to see it like that, you can do that. And actually, if we closed the parentheses here, and ran this, I want to show you what it would look like. Sorry, it's taking a minute to generate. You could see all these different columns that get added. So we have the confidence interval. There's the standardized confidence interval, which we may not even want to see. It's the same thing as the confidence interval, right? There's the statistic, the p-value. which it bolds the p-value if it is less than 0.05 by default. There's the degrees of freedom, which we don't really need to see. That's really just the degrees of freedom at the model level. It's not separately for each of these. So the next thing that we can add to this, if you put another comma, we can tell it, use this column order equals function to not only reorder the columns, but also tell it what order, what not to include. So it will only include the things that we tell it to do here. So for instance, maybe we don't really want the degrees of freedom to show up there. So you could just take it out here, but since we're adding this, we can just do that here. And remember, the C function allows us to give a list of things that we want. So we're going to say C open parentheses, and inside the parentheses here, we're going to tell it to include EST and quotation marks. Everything is in quotation marks with commas separating the sets of things. So EST for the estimates, STD for the standardized estimate, STD EST, sorry, the STD EST is standardized estimate. STD SE for standard error, stat for the t-score, CI for the confidence interval, P for the p-value. And actually, I tried to include this. It doesn't work. I'm going to take that out. I think that only gets included if you have multiple models. Sorry about that. So then if we were to end here, it would put them in this order. So the rest of this is all about cleaning up the way that it looks. So pred labels, that means what do we want it to say on the left column here? Intercept, PISA ESCS, PISA female. We don't want it to say, we don't need to say PISA dollar. So here we can say pred.labels equals C and then put intercept in parentheses. That is how it shows up in tables. You wouldn't have to put it in parentheses though. You could just say intercept, ESCS, and female. And it will replace those sets of text with what we type in here for those 3 rows. DV labels. This allows us to change the label that's at the top that says PISA dollar PV1 math. So here I just called it multiple regression onto PV1 math. String pred. So that is the first column here. The predictors column where it says predictors. So string pred equals, and in quotation marks, we can put coefficient. Or you could put variable name or something like that. String.est, that's the estimate column. So we can just type estimate there. We don't need an S on the end. String std, that is the standardized value. So we can call that beta. We don't need to have std.beta. String.stat, we know that this is a t-score because it's a regression, a linear regression. So we can just put t. And then p-style. Right now it's showing p and it says less than 0.001. But we can change that to say scientific so that it says what it does on the screen normally. It puts it in scientific notation so that we get an idea of how much smaller than 0.001 is this value, or a more exact value for the p-value. You can also change this to be all kinds of other things. You could have it show you stars next to estimates to indicate the p-value. So there's other things you can tinker with here to make your table look the way you want. So if we run this whole thing, we're going to get a pretty nice looking table. And my only beef with this is that I can't include the F statistic and p-value, associated p-value underneath the table where the R squared is. You can see here that it looks a lot nicer with the p-value here on the right. 3.734e negative 24. So that tells you there's a lot of zeros there. Basically, the intercept in the CS value, it approximated it to be 0. It was so far out. It probably couldn't go past, it's probably past 100 digits to the right. The standard errors here are in parentheses. T-scores, confidence intervals for those T-scores, p-values. So it's a nice looking table that includes almost all the information you would want, and you would need to include the F statistic and p-value in your write-up of this. So that's how we can use R to make things look nicer, and hopefully you've learned something from this video. Let me know what else you're thinking about this, or if you hit any problems.